Welcome to my online lecture on mathematical and engineering modeling of sprays. As you can see, the title of this lecture is rather general. And by suggesting this title, I want to emphasize that my focus will be on the general philosophy of modeling, of both mathematical and engineering modeling, rather than on discussing a specific engineering problem of the modeling of sprays. I hope that this philosophy and this approach to modeling could be shared by other colleagues working in other fields of engineering, biological modeling, data analysis, and similar fields. And this is the plan of my lecture. I will start with the background, then I will discuss the meaning of terms, give you a couple of examples of how our approach is realized in practical problems, and then I will focus on one specific problem, namely microexplosions in composite droplets, which is particularly important for engineering applications. When speaking about the background, I will start with a brief overview of a paper prepared by Michael Berry, Emeritus Professor from the University of Bristol. This paper is entitled True but Not Real. And the author tried to focus on two concepts, the concept of true and concept of real. These concepts are obviously different, but sometimes the difference between them is not well perceived by the community. When the first example, which is given in this paper, is the phenomenon of mirage. The mirages can be seen, say, in the desert, but at the same time, they're not true. They can be seen as real, but they don't reflect a true phenomenon. In a similar way, we can consider rainbows. The phenomenon of rainbows was discussed back by Descartes several centuries ago, and he taught us that rainbows are illusions. Here are no colored arcs in the sky. Each raindrop emits light focused into a bright cone, and we looking up see brightly lit only those droplets whose light cones intersect our eyes. So each person can see its own rainbow. So a rainbow is real, but it doesn't reflect the real physics. We see the real phenomenon, but not real physics behind it. At the same time, rainbow physics is true, but it is not real. So we come across two terms, true and real. Real is something that we can see, we can touch, we can understand. True is something hidden from our perception in most cases. And there is a parallel between these two concepts and the concepts of reality and modeling. We don't know much about reality, and the only way how we can perceive it is via modeling. We can't understand each and every detail of reality, but at the same time, we can approach it rather closely by developing more and more sophisticated models. And now we can move to the definition of terms. So mathematical modeling can be defined as a description of the process, engineering, environmental, biological, in terms of mathematical equations. Engineering modeling is also a description of engineering process in terms of mathematical equations. If we use this definition, then mathematical modeling incorporates engineering modeling. But this is not the only approach to the defining of these terms. An alternative approach in the alternative approach, mathematical modeling is perceived as equivalent of engineering mathematics, and engineering modeling is equivalent of computational fluid dynamics. Engineering mathematics is essentially modeling of individual processes. These could be numerical or analytical. Example, modeling of deformation of individual droplets. Computation fluid dynamics is a focus on modeling of realistic engineering systems. These modeling can be performed only numerically. And example is modeling of diesel engines. These concepts of engineering mathematics and computation fluid dynamics were discussed in length during my previous lectures, and I'm not going to repeat these presentation. But what is important for us is that there is no contradiction between engineering mathematics and computation fluid dynamics. They complement each other. The most constructive and approach to the analysis of engineering systems requires a combined approach using the methods of engineering mathematics and computational fluid dynamics. And this will be illustrated using two examples. One example is focus on fully Lagrangian approach to tracking droplets or particles. The conventional approach which is used in most research and commercial computation fluid dynamics codes is based on the so-called Eulerian and Lagrangian approaches, where continuous phase is modeled using Eulerian approach and Lagrangian phase is modeled using and dispersed phase is modeled using Lagrangian approach. At the same time, this approach creates problems when we intend to find the time evolution of particle or droplet densities. And to tackle this problem, a new approach called full Lagrangian approach has been developed. And here are the basic equations referring to the full Lagrangian approach. In what we tried to do in our previous research program is to incorporate the full Lagrangian approach into computation fluid dynamics codes. And ANSYS Fluent was used as a testing ground for this. So here we can see the results of incorporation of this model into Fluent, and it shows the distribution of number density of droplets of various sizes. And this is the reference of the paper where the details of these incorporation and testing are described. This slide, you can see a comparison between the prediction of the model and the actual observations in internal combustion engines. Here we have the time slots, 1, 1.5, and 2 milliseconds from the start of injection. And we consider time evolution of more than 10,000 droplets with diameters between 1 micron and 30 microns. Another example refers to effective thermoconductivity and discrete component model. So these, in most of commercial computational fluid dynamics codes, a number of simplified assumptions are used. For example, the temperature gradient inside droplets were ignored, and also the droplets were considered as opaque gray spheres. That means that the penetration of thermal radiation and volumetric heating by thermal radiation of droplets were ignored. Also, the effects of diffusion of species inside droplets were not considered. In a series of our publications, we tried to take into account these effects. Moreover, to simplify the problem, we used analytical solutions to both these equations, and these analytical solutions were incorporated into numerical codes. Here we can see the reference to the paper where the results of incorporation of both these models into ANSYS Fluent are described. And now we focus on the main topic of our lecture, modeling of microexplosions. Here you can see a typical video of what happens with the droplets, with the fuel droplets in which water is added. The main stimulus of adding water is into fuel, including automotive fuel, is to stimulate droplet disintegration. And the disintegration leads to the rapid evaporation and mixing of fuel vapor and air mixture. Here we can see some images which of microexplosions which were obtained in our experiments. On this image, you can see puffing of droplets, which typically precedes microexplosions. And here we can see properly fully developed microexplosions. And these images were taken from this paper. The most rigorous approach to modeling of the phenomena is based on the direct numerical simulation. Here we can see some examples of these direct numerical simulations taken from the paper by my colleagues Shinyo and others. Direct numerical simulation obviously can capture a lot of fine features of the process which couldn't be captured using any other methods. But at the same time, the picture which you can see would vary a lot if you change slightly the initial and boundary conditions inside the droplet. For example, if you consider the location of water inside the droplet in different places. And also this approach cannot possibly be used in conjunction with the computation fluid dynamics codes, because you cannot incorporate direct numerical simulation into engineering computation fluid dynamics codes. In a series of our papers, we developed a simple approach to describe this phenomenon. And I will start with a very simple model. In this very simple model, it is assumed that a water subdroplet of radius RW is located exactly in the center of a spherical fuel droplet of radius RD. The temperature at water-fuel interface is TW, and the temperature at the surface of the droplet is Ts. And the heating process of the droplet is described by the heat conduction equation, where the value of kappa thermal diffusivity appears to be different inside the water and inside the fuel. Also, the initial temperatures could be different in the general case inside the fuel and inside the droplet, and you have continuity conditions at the water-fuel interface. At the surface of the droplet, a simple Dirichlet condition was used. In other words, the temperature at the surface of the droplet was fixed. And this equation with these boundary and initial conditions was solved analytically, subject to a number of assumptions. So these are the key assumptions which were used. Firstly, the temperature of the droplet surface is assumed to be constant during the whole period of droplet heating, not just during individual time steps. The effects of droplet evaporation and swelling are ignored. The thermodynamic properties, liquid thermal conductivity, heat capacity, and density, are set at the initial droplet temperature, set at the initial droplet temperature. And then it was assumed that microexplosion starts when the temperature of water or temperature at the water-fuel interface is equal to the boiling temperature of water. So using this assumption, the analytical solution was obtained. And this analytical solution is valid for the whole period of droplet heating. And then it was applied to a specific case of droplet microexplosion, which is with the input parameters described in this table. I just want to draw attention that the droplets under consideration were rather small. They were less than their radius were less than 100 microns. And the water content of the droplet was 15%. And then incorporating these input parameters into the analytical solution allowed us to calculate the distribution of temperature inside the droplets at various time instants. And as you can see from this graph, when time instant was equal to 0.5 milliseconds, then the temperature at the water fuel interface becomes equal to water boiling temperature. This model was validated using experimental results. And as you can see, so what we try to validate is the dependence of time to puffing, which leads to microexplosion, at various initial droplet diameters. And as you can see, the droplet predicts the increase of time to puffing with the increase of the initial droplet diameter. And this is consistent with actual observations, which can be seen in this figure. This model is described in our paper published last year. And but at the same time, these assumptions which were used in developing the model described in that paper appears to be very stringent, and it would be tempting for us to relax at least some of these assumptions. And this is something that we did in a new simple model of the phenomenon. For example, the assumption that the droplet surface temperature is fixed is replaced by the assumption that the surface temperature is allowed to vary with time. That means that the Dirichlet boundary condition was replaced with the Robin boundary condition. Also, in contrast to the previous model, the effects of droplet evaporation and swelling were taken into account. Also, in contrast to the previous model, the temperature and time dependence of thermodynamic and transport properties were taken into account. And what is most important from our point of view is that the start of microexplosion or puffing was associated not with the time instant when the temperature at the water-fuel interface was equal to the boiling temperature of water, but with the time instant when the temperature at this interface was equal to the nucleation temperature. And this nucleation temperature can be different from the temperature, from the boiling temperature. And in this case, but most of other assumptions of the previous models were still there. For example, this assumption that the water subdroplet is located exactly in the center of the fuel droplet is still used in the new model. Also, the new model is based on the same equation for transient heat transfer inside the droplet as in the previous model. In contrast to the previous model, this equation is not solved during the whole period of droplet heating, but it is solved at each individual time step. And the results of the solution were incorporated into the numerical code. And also, in contrast to the previous model, we use not the Dirichlet, but the Robin boundary conditions. And also the effects of droplet evaporations are taken into account. And as a result of these assumptions allowed us to obtain a more general expression for the distribution of temperature inside the droplet at various time instants. And these are given by these formula. I'm not going to describe the meaning of these terms, but they are presented here at this slide. And when this model was applied, to the heating and evaporation, to microexplosion of heated and evaporated droplets. The droplets which are considered are rather large ones, and the radius of these droplet was equal. Initial radius of these droplet was equal to 1.33 millimeters. And as you can see, for these droplets, we predicted the time to puffing equal to 8.2 seconds. Assuming for the time being that the puffing starts at the time instant when the temperature at the interface of water and fuel is equal to the boiling temperature of water. But now it is we can recall that the actual boiling happens not at boiling temperature, but the so-called nucleation temperature, which depends on the speed at which the temperature at the interface raises. And here we can see the approximation of the dependence on nucleation temperature on the heating rate obtained experimentally. These are different symbols, and also using the approximation which is shown in these by this formula. This approximation is valid in the range of temperature, in the range of heating rates between 100 and 1 million. If this heating rate is less than 300, then a different approximation was used. And this approximation is also supported by the available experimental data. Now, to use this approximation, we need to find the values of heating rate at the interface, at the water-fuel interface. And here we have the values of this heating rate for two models, which doesn't take into account the effect of swelling. And now we can obtain two curves. First curve, which is the temperature at the water-fuel interface, and this is described by a thick solid curve. Another curve, which is shown here, is a time evolution of nucleation temperature. The nucleation temperature is calculated using the values of heating rate, that is a derivative of temperature with respect to time, and using the correlations which we considered earlier. And on the same plot, we showed the line corresponding to the boiling temperature. And as you can see, there is a visible difference between the time to puffing is described by the intersection of these two curves. The intersection between the solid curve and this one, referring to nucleation temperature, gives us the corresponding value of time to puffing. And the intersection of this solid curve with the line corresponding to boiling temperature will give us slightly smaller value of the time to puffing. And these values are equal to 8.5 and 8.2 seconds, and they need to be taken into account in refined analysis. And unfortunately, there is not a good agreement between experimental results and the prediction of the model. The model predicts smaller time to puffing. And this is attributed to the main limitation of the model, that the water droplet is located exactly in the center of the fuel droplet. If it is located off-center, then the time to puffing would be much less than the one predicted by our model. And the results, preliminary results, were published in our early papers, published early this year, and the full description of the model is given in our recent paper submitted for publication in International Journal Heat and Mass Transfer. And these are the funding bodies which are supported this research. And I thank you for your attention. Thank you very much.